Let's begin today's session. In the last lecture, we have been discussing about relative motion. So we'll continue from that point onwards today.
Yes, sir.
Okay, so far we have discussed about the relative motion parameters. And in that we have seen relative position defined in this manner, that the position vector of a body B with respect to another body A is given by the formula RB minus RA, where RB and RA are the positions in ground frame, and RB is the relative position of B with respect to A. And
Yes.
from that, we saw that, yes, the displacement, the relative displacement was similarly defined. Relative displacement of B with respect to A is equal to displacement of B minus displacement of A in the ground frame. And further, on differentiation of either of these, we get the relative velocity formula. It is velocity of B with respect to A is equal to velocity of B minus velocity of A. So let's start today with some applications of these. Then we will come to relative acceleration also. Should be the last of these definitions. So let us look at an example like this, that we have a particle A starts from the origin of the xy plane at t equal to 0 with initial velocity of, let us say, 90 kilometers per hour, okay, along the x-axis, and has zero acceleration. Now another particle B also starts from the origin at t equal to 0 with now this time it has an initial velocity of magnitude 150 kilometers per hour, but at 53 degrees with respect to the x-axis. Okay. Also with zero acceleration.
Sir,
Yes.
I had a doubt. Like, if we say like VAB, then it would mean that velocity of A when the observer is observing it from B. Right?
Yeah.
B.
Yeah. If we say VA comma B, then this is a relative velocity of of A with respect to B. So our observer is at B and we are observing A. Understood this point, no?
Yes, sir.
Whereas here when we have written B comma A, this is a relative velocity of B with respect to A, kind of situation. So first of all, find the relative velocity of B with respect to A. Second, find the positions of A and B after 1 hour, and show that displacement of B with respect to A is equal to velocity of B with respect to A multiplied by time. From part 2. Okay, so just first of all, make a diagram in the XY plane and try to understand the example given to you. Try to understand the direction of B's motion and how they will move relative to each other from the diagram, and then systematically answer the parts 1, 2, and 3.
So for position of B, we have to give it in component form, I cap, J cap, or like mod karke.
That's up to you. You can give in I cap, J cap form, or you can say that it is, so many kilometers in such a direction. But the information should be such that you have both magnitude and direction.
Okay.
So you can give it in coordinates form also, that X coordinate is so much, Y coordinate is so much, or you can give it as a I cap, J cap notation.
So that X coordinate and Y coordinate is same only as I cap, J cap, I guess. Yeah.
Yeah. Yes, that is correct. Vedant and Jinendra. Yes, Vedant, that is also correct. Okay, so we will both apply the component algebra as well as understand it geometrically in the XY plane. So what is happening is that one of them starts from here at t equal to 0.
Sir, for B we have to find the velocity along x-axis. No?
Yes. The A's velocity is directly 90 I cap, right, in kilometers per hour. But B's velocity 150 meters per second. At an angle of 53, right? An angle of 53. So this is 150 in magnitude, and this angle is 53. So this is B's velocity. And this is where they start from. So at the given time, what will happen? Let's say A is somewhere here. So in 1 hour, displacement of A so A's position will become 90, 0, and displacement of B so that will be 90 I cap plus 120 J cap. So B's position would have become 90, 120. So if A is located here at the coordinates 90, 0, B would be located somewhere here at 90, 120. So you can see in the diagram that the relative displacement of B with respect to A, that has become this vector. at t equal to 1 hour. So first of all, from this earlier data, this one and this one, you can see the answer to the first part. Relative velocity of B with respect to A is 120 J cap in kilometers per hour.
Yes,
Okay,
sir.
then second part, you can see that the positions after 1 hour are this. Okay. Now third part, you can see that displacement of B with respect to A is equal to the vector from A to B, that is 90,0 to 90,120 at t equal to 1 hour. So from the diagram, you 120 J cap in kilometers. But also you can see since acceleration of A and B is 0, so therefore relative displacement can also be expressed as relative velocity into time. So you can see that in 1 hour, it's 120 J cap into 1 hour. It's 120 J cap kilometers per hour into 1 hour. So it is 120 J cap. Kilometers, which agrees with what we are seeing geometrically from the diagram also. Okay, so that was the whole point of this question. The third part, to show that what you are seeing from the diagram or from the coordinates, the relative displacement 120 J cap, it is also equal to the relative velocity into time. Yeah, you can convert it and do it also. That's correct. Okay, but here it's all right. You can give the answers in kilometers and kilometers per hour. It's fine.
Yes, sir. Actually, I changed the whole thing into meter per second. That is why my units are little bigger.
Okay. Okay. It's fine. Okay, now let's look at another example of relative motion with the application of the formula of relative velocity. So this is again a very common everyday occurrence that we see. Relative motion of rainfall as seen from a moving frame. So in our particular example, let us say rain is falling vertically. The actual velocity of rain with respect to ground is vertically downwards at some velocity VR like this. Rain falls vertically with velocity equal to, let us say, 40 meters per second with respect to the ground frame. So if a person is in a vehicle moving horizontally at, let's say, velocity of the car 30 meters per second, find the magnitude of the relative velocity of the rain with respect to that car's frame, and find the angle at which this relative velocity is slanted with respect to the vertical. So we'll discuss this question next. Okay. So here, this quantity is the relative velocity of rain with respect to the car. Okay. Or with respect to the person. Moving in a car with a velocity of vc. Okay, so let's assume the car is moving along the horizontal direction like this.
Sir,
At 30 meters per second. Yes,
sir, magnitude is 50.
yes, that's correct. Yes, Jinendra, your answer is correct for relative velocities angle also. So there are a couple of ways we can do this. One is we can just understand this using vector algebra. If we take our y-axis to be vertical and x so the car is moving like this. Okay, and the velocity of the rain is like this. Okay, so the velocity of the rain with respect to the car like this. Okay, so this vector you can see will become like this. So you can see that the magnitude of this and we want to find out this angle. So this angle we can see is such that this component is 30, this component is 40. So theta is equal to 37 degrees with respect to vertical slant. Okay. So this is one way of doing the question using the component algebra. The other way of doing the question is geometrically. Geometrically, we can do the question this way, that we draw the velocity of the car like this. Which is the velocity of the rain in the ground frame. So now you can see that since this angle is 90, and now with respect to the vertical, this angle is theta. That's the same as this angle. Okay, people. So hope this example is clear to all of you. Now,
Yes, sir.
yeah. Okay. Now moving on to the definition of the final parameter, that is relative acceleration. So as we have seen in kinematics before, acceleration is defined as rate of change of velocity with respect to time. So accordingly, relative acceleration, let's say of b with respect to a, will become rate of change d by dt of relative velocity of b with respect to a. So relative acceleration equals to the rate of change of relative velocity with respect to time. Now this becomes doubly important because not only will understand how to solve kinematics problems where two objects are accelerating and to solve the motion of one with respect to the other, but it will also give us a way of understanding the whole concept of Newton's second law application in an accelerated frame and the reason why pseudo force has to be included in that equation. So explanation of that also will come from the concept of relative acceleration. But before that, let's derive the formula. So this is the definition. Okay. Now the formula will accordingly become, when we expand the right hand side, rate of change of velocity of b with respect to a, when we expand this as the instantaneous velocity of b in the ground frame, instantaneous velocity of a in the ground frame. We already know this formula, that relative velocity of b with respect to a is vb minus va. So now we just have to take the differentiation operator inside. So next step, it becomes rate of change of vb minus rate of change of va. And we know that by definition, rate of change of vb is acceleration of b in the ground frame. And similarly, this is acceleration of a. So we get another symmetrical kind of definition, that or formula, acceleration of b with respect to a becomes the acceleration of b minus the acceleration of a. Okay, so just a simple example of this. Suppose we have a situation where we are inside an elevator which is accelerating downwards at the rate of A. Say
Yes.
AE, that is the acceleration of the elevator. Suppose that is 2 meters per second square. Okay. And now an object like a a bolt or something comes off the ceiling of the elevator and starts falling freely. So a particle P and another observer B is on the ground at rest. So a particle P comes off the ceiling of the elevator and is in free fall. Take G equal to 10 meters per second square and assume there is no air drag kind of force on P. Only gravity acts on. Okay. So we have to find the acceleration of the particle P as seen from the ground frame. That is the observer B. It's that acceleration we have to find out. How much is the acceleration of the particle P in the ground frame? And we have to also find out as seen in the elevator's frame. That is the observer A will be seeing that. So the acceleration of the particle P in the elevator's frame, how much that will be. So as you can see here, what we can do is we can just understand that downward direction is our y-axis. So we can write the acceleration of the elevator in vector notation as what? 2i cap.
J cap.
Or we can say, sorry, 2j cap, my mistake. 2j cap in meters per second square. Or we can just say that it is plus 2 meters per second square downwards. Okay. And the acceleration of the particle in the ground frame will be what? It will be gravity only. Okay. So the acceleration of the particle in the ground frame will be gravity. So it will be 10 j cap in meters per second square. Okay. Or in scalar form, we can write it as plus 10 meters per second square, positive direction being downwards. Okay. So therefore, so why this happens? This is because in inertial frame, okay, for the FBD, the free body diagram of the particle, okay, only gravitational force acts on it. Only gravity acts on it. There's nothing else pulling the particle down. There's only gravity. So its acceleration should be mg divided by m. So its acceleration should be g. Okay. However, what is going to happen therefore now is that the acceleration of the particle in the elevator stream, that is as seen by E, that is going to change. Okay. This is going to be as seen by B because he is at rest on the ground. Is this observer here? So this one is going to be acceleration of the particle in the ground frame minus the acceleration of the elevator. So this will become 8 j cap in meters per second square. Or in scalar form, we can write this as 8 meters per second square downwards. Okay, so hope this example is clear. Intuitively also, like the floor of the elevator is going down at 2 meters per second square and the particle is going down at 10. So with respect to the floor of the elevator, the particle will be seen to be coming at how much acceleration? Less than that, because it's going in the downward direction. So 10 minus 2, 8.
Sir, you are not audible.
Sir is not saying anything.
Sir is now saying.
Sir is not saying anything for the moment.
Clear it out.
No, sir.
This clear?
Yes, sir.
Okay, now see, you understood the concept of relative acceleration, but also we'll see how to understand this from Newton's laws point of view. Okay, so if we do this by application of Newton's second law, so you'll see that one is we can make the free body diagram in the ground frame, and that is our so-called inertial frame. So in inertial frame, when we make the free body diagram of that particle as it is in free fall, there'll be only one force acting on it. There'll be gravitational force. Nothing else or nobody else is applying any force on it. So mg is there. So with respect to ground or inertial frame, which was basically my observer P on the ground, its acceleration seen will be like this. That is the acceleration of the particle. So mg, that is the net force, is equal to mass into acceleration. So you can see the acceleration of the particle is 10 meters per second square downwards. But I can also do one thing. I can make the FBD in the elevator's frame. Now the elevator's frame is an accelerated frame. So therefore it is what we call a non-inertial frame. So in that non-inertial frame, what is happening is our non-inertial observer, let's say A, he himself is going down with an acceleration of AE. So on the particle now, there is pseudo force. Okay. And pseudo force's direction should be opposite to the acceleration of the frame, and the magnitude should be. So pseudo force, remember, given by the equation minus of m into A, or A naught, let's say, where A naught is the acceleration of the non-inertial frame, not the acceleration of the particle, but the acceleration of the non-inertial frame. So here is AE downwards. So pseudo force is MAE upwards. So that's how this is done. Okay, and of course, apart from that, we have the real force, which is only one in number, mg, acting on it. And with respect to this frame now, it has an acceleration which is like this, acceleration of the particle with respect to E. So this is the acceleration of the particle P in the non-inertial frame, or you can say relative to the elevator. So you can see how basically it is nothing but a concept of relative acceleration. The concept of pseudo force is actually like a concept of relative acceleration. So when we say that net force is equal to mass into acceleration, here the net force will become mg minus the pseudo force. But the acceleration on the other side will be which acceleration? It will be the relative acceleration. So you can see that eight meters per second square downwards. Okay. So this thing which I've shown in a one-dimensional case over here, that is a straight line motion case, we can also show it in general vector format. Okay. So hopefully this should also give you a good understanding of the understanding of pseudo force concept.
Sir,
Yes.
sir, what is written in bracket in second point? Which frame is there? Acceleration.
Free body diagram in elevator's frame, that is the accelerated frame, or it is a non-inertial frame. The elevator's frame is an accelerated frame with respect to ground.
Sir.
So by definition, any frame which has acceleration becomes what kind of frame? It becomes a non-inertial.
Non-inertial.
So this concept is coming from your Newton's laws chapter, right? Understood this point?
Yes, sir.
Okay. Okay, now let's see a.
Can I scroll up for it?
Okay.
Just a
Yeah, just scrolling. Okay, done with this?
Yep.
Okay. Now let us look at another example of the same kind of situation, basically. An elevator, but this time the elevator is accelerated upwards. Some unknown acceleration. Now there's a person inside the elevator. So what he observes is that the person inside the elevator observes that a bolt comes off the ceiling at t equal to 0. Okay. When the elevator starts from rest, moving upwards at constant acceleration, AE, and hits the floor at t equal to 1 second. Take g equal to 1 meter per second square. So find also the floor to ceiling height of the elevator is 6 meters. It's a transport elevator, let's say, so it's a very high elevator. 6 meters, about 18 feet, so it's almost close to 2 stories high. So it's one of those logistical transport elevators, so very high ceiling. So we have to find, first of all, the acceleration of the elevator. Secondly, the displacement of the bolt B.
G is 10, right?
Yes, G is 10 meters per second square. In the ground frame and in the elevator's frame. Okay, so who all have got the answer, please send me quickly. What is the easiest way to do the question? Yes, very good, Vedant, that's correct. Jinendra and Vedant, that's correct. Yeah, so tell me, what is the easiest way to handle the question? What I should do first to find AE?
So first we'll take h is equal to ut half at square. You can use that formula.
But in which frame you're taking? That is the main thing.
I'm taking the non-inertial frame.
हाँ, किसके फ्रेम में आसान है देखो, वो it is in the frame of the elevator, because in the elevator's frame I know exactly how much displacement it's making. It's going from ceiling to floor and I'm inside the elevator, no? So the ceiling to floor distance is fixed. So that is how much, that is h, which is given to me as 6 meters. So that's why that's easy. It's a relative motion concept also, no? Like you can apply Newton's laws like you're saying, non-inertial frame and all that, but even that is not required. What you can do is you can just see that in the elevator's frame, what is happening is that t equal to 0, the bolt is starting with initial velocity equal to 0 and eventually it is falling onto the ground at time 1 second after having made a displacement of 6 meters. But while it is making this displacement, its acceleration is like this. Okay. So acceleration of the bolt is g downwards. Okay. And acceleration of the elevator is AE upwards. Okay. So what is the acceleration? Sorry, AE downwards. Oh yeah, it is AE upwards. So what is the acceleration of the bolt with respect to the elevator? Okay. It is acceleration of the bolt minus acceleration of the elevator. So it will actually become G plus AE downwards. When I do it vector wise now, you can see. I take y-axis downwards. So the y-axis is downwards. So sorry, let's take it as minus AE j cap because it's upwards. Okay, so this will become 10 plus AE j cap because I've taken y-axis downwards. So plus. And initial velocity of bolt with respect to axis is 0. So displacement should be equal to ut plus half at square. So using that relation here, displacement of the bolt with respect to the elevator should become half of g plus AE into t square. So basically, so this should be equal to 6 meters at a time of 1 second. So from this we'll get, well, which means the acceleration of the elevator is 2 meters per second. So this same thing that I've done, you can also do by using Newton's laws, but here we will, from this point onwards, use relative motion instead of using Newton's laws. Yes, very good, that's correct, Jiren. And you can understand that for the second question, one part we have already answered. For the second question, B part we already know that the displacement of the bolt in the elevator's frame is equal to h j cap, where I've taken y-axis downwards, or displacement of bolt with respect to elevator is 6 meters downwards, because in the elevator's frame, okay, ceiling to floor is a fixed distance of h equal to 6 meters. That is explanation. Okay. But now to understand the A part of this, that is what is the displacement of the bolt in the ground frame, we have to separately understand how much the elevator is moving and how much the bolt is moving. Because if you observe this from the ground frame, when the bolt starts falling, the bolt is falling with G, but the floor of the elevator is going up at AE. So they meet somewhere in between. Okay, so the bolt doesn't actually fall through 6 meters. Because in the time when the bolt has fallen for 1 second, the floor of the elevator has also gone up for 1 second. Okay, so people, this is about relative acceleration in this kind of situation. So next, let us look at an example like this, where what is happening is that two particles move in the xy plane such that A starts from rest at t equal to 0 with uniform acceleration equal to 2I cap. B starts, or B is moving with uniform velocity of VB equal to, let us say, 10I cap plus 15J cap in meters per second. Wow. So find the relative acceleration of A with respect to B as a function of time. Then the relative velocity of A with respect to B, again as a function of time. And 3, the relative displacement of A with respect to B from t equal to 0 to t equal to 2 seconds. In 2 seconds of motion, what is the relative displacement between the two particles? Okay, so through this question, we will look at the application of all the three concepts: relative acceleration, relative velocity, and relative displacement.
Sir, I have sent like all three ones.
Yes, I will just review the answers. Yes, very good. That's correct. So Jinendra and Vedant, your first and second answers are correct, both of you. And Jinendra, your third answer, I will just check. Just give me a moment. Yes, it's correct. Okay, so first part you can see that acceleration of A is 2 I cap in meters per second square, and it is given to us that acceleration of B is 0 because it's moving uniformly. It says it moves with uniform velocity, so its acceleration is 0. So therefore, acceleration of A with respect to B will become acceleration of A in ground frame minus acceleration of B in ground frame. So this relative acceleration is only 2 I cap, which is the ground frame acceleration of A also. Okay, and it is a uniform relative acceleration. So it is not a function of time, or it does not vary with time. Yes, that's correct for the third answer.
So me.
Yeah. So now for relative velocity, we have two options. One is what we can do is we can write velocity of A as a function of time. It will be 2t I cap, using the fact that V is equal to U plus AT for A. So you understand that VA is equal to 0 plus 2t along the x-axis because the acceleration is along the x-axis. And velocity of B is given to us, it is uniform 10 I cap plus 15 J cap in meters per second. Okay. So using this now we can see that, okay, the velocity of A with respect to B is at any instant the velocity of A minus the velocity of B, which is uniform. So it is 2t I cap minus of 10 I cap plus 15 J cap. So that will become 2t minus 10 I cap minus 15 J cap in meters per second. So this is one way of calculating the relative velocity. Yeah, I'll discuss another way also, but this is one way. And probably this is the simplest way of understanding it.
So,
Yes,
if we integrate the acceleration, we'll get the velocity, right?
yes, you can do that also.
Use it here.
Yeah, that can also be done. Okay, so you can also do in this way that now at t equal to 0, what is the initial velocity of A with respect to B? It is the initial velocity of A minus the initial velocity of B. Now A
Yes.
started from rest, okay, and B's velocity is 10 I cap plus 15 J cap. So the initial velocity of A with respect to B is minus 10 I cap plus minus 15 J cap in meters per second. And I also know that the acceleration of A with respect to B, I've seen that before, it is 2 I cap in meters per second square. So I can use this and this to now understand that the velocity of A with respect to B at some time t, it has some x component plus some y component. So for the x component, we'll just use ux plus AT, like this. Okay. So this ux will be this value -10, and AT will be 2t, and Vy similarly uy plus ay into t. So uy we can see is -15, but ay is 0, doesn't have any y component. So from this we can now see that okay, the velocity of A with respect to B at any time. So because it's a uniform acceleration, right? So to answer your question, we don't really need to do an integration. We can just use the standard equations, ut plus half at square for displacement, or u plus at for velocity. But this is basically equivalent to using integration only, because the standard equations have been derived from integration, as you know.
Yes.
Okay, sir.
Okay, so now let us look at the relative displacement concept. So that also we can look at either by looking at individual displacements of A and B, and then working it out that way. So the third part, relative displacement S of A with respect to B after 2 seconds. Okay, So one is we can do like this, that from t equal to 0 to t equal to 2 seconds, what is A's individual displacement? Okay. And what is B's individual displacement? And then we can calculate displacement of A with respect to B as displacement of A minus displacement of B. So A, what it's doing uniformly accelerated 1D motion, okay, along x-axis. So A's initial velocity is 0, A's acceleration is 2. So A's displacement is 0 plus half into 2 into t square. So A's displacement is t square I cap as a function of time. So therefore A's displacement is 4 I cap at t equal to 2 seconds. Now similarly, what is B's displacement? Let's understand that. So B is in uniform motion, that is uniform velocity, which was given to us as 10 I cap plus 15 j cap. So B's displacement in the ground frame should be equal to velocity into time. So therefore, at t equal to 2 seconds, B's individual displacement is seconds. So B's individual displacement is 20 I cap plus 30 j cap. So now using this value and this value, we can see that the relative displacement of A with respect to B will become the difference of these. Okay. So that will become minus 16 I cap plus 30 j cap in meters.
Why is it plus 30? It should be minus 30 JK. Right?
Minus 30, yes. Correct. It should be minus 30. Just make the correction here. Okay, people. So hope this example is clear to all of you. Right.
Yes,
So with
sir.
that, we conclude.
Yes.
Yeah, we conclude today's session. So we are done with the
Thank you,
concepts
sir.
of relative motion. Yes. Next lecture, we will look at doubts and questions, particularly from HC Verma and the module. Okay, so finish up maximum questions of HC Verma at least before the next lecture.
Sir,
Yeah.
of this, yes, sir. Okay.
Kinematics, huh? Full kinematics now, that entire
Yeah.
chapter. So have a nice day. That's it. Yeah.
We also discussed the questions from the major test.
Yeah, I'll discuss in the next lecture. Okay.
Okay, sir.
By then your advanced will also be done, so I'll discuss.
Yes, sir.
Okay, sir. Thank you, sir.
Sir, in HC1, do we have questions based on projection on an inclined plane?
No, HC1 में नहीं है. Those questions are there in the worksheet which I've given you in projectile motion. And
Sir,
also,
I've done almost till 22nd or 23rd. Up till now, I've come across the projection over an inclined plane.
Sir,
yeah,
well,
there are less questions.
In worksheet, it's not clear.
And module maybe there is one
yes, sir.
section.
In module it is there.
In module also. It is there.
Okay, sir.
Just go through the module 1 kinematics part. It is there. Okay?
Okay, sir. Okay. Got it, sir.
Okay. Plus later also I'll be giving a revision worksheet when we finish all this now. So I'll give more questions.
Okay, sir.
Inclined plane one is more common in advanced papers, right? Normal, like mains.
Yeah, you can say like that. I mean, it is like rare for JEE mains. You can say like that. Okay?
Yes, sir.
But it's within syllabus. It's within syllabus even for JEE mains. So prepare it properly.
Yes.
Okay?
Okay.
Thank you, sir. Bye, sir. Have a nice day, sir.
Okay, people. Bye. Have a nice day.
Bye, sir.